Definite integrals. Okay, so this is a definite integral. This is the notation for it, guys. I know we've already written it a lot, but let's put some words to our yeah, whatever. This is the upper bound. Now normally we start with the lower bound, okay? I'm gonna put lower bound over here. You always start with the lower bound because usually it goes left to right. That's how it reads. It goes small number to big number. Okay, then the inside right here, this is your integrand. And this is what you're taking, this guy. That's what you're taking the integral with respect to. So I'm going to call this variable of integration. Because of where we're at and working on this concept, I think that you guys can probably do all this stuff on your own. But I'm going to do it with you right now just to kind of speed it up. So this one right here, it says, now there are a lot of things, meanings of the integral that it can take on. Okay, here we are considering how it represents the area under a curve. And so I gave you guys a cute little curve right here. I'm not giving you guys the rules for the function, just the graph itself. And so can you guys find the answer to this? What is the area from 3 to 7 of this function? And so you would come over here to your graph, and at 3, that's right here. I'm gonna draw a little dotted line right there, and I'm gonna go to 7 and draw a little dotted line right there. I'm gonna shade this area in. Can you find the area of that area? I'll give you guys a minute to do that. So instead of counting boxes like some of you guys out there, I'm going to divide this into 2 trapezoids. This is my first trapezoid. You see my first trapezoid? Okay, I'm going to say whatever the height is for that and whatever the height is for that. Let's see, that one's kind of easy. That height is up to, does it go up to 6? That's a 6. And then this one's right here is like 3/2 or 1 1/2. But I like improper fractions. And what is this line right here that's connecting my 2 bases? That's your height, or you can know, or better known as delta x. What's our number there? So that's 3. Okay, so now we're going to do a trapezoid formula for that. And then we also have another trapezoid right here. Let's do the same thing. This is 6. This looks like it's a 1, 2, 3, 4. So I'm going to do 4 right there. And it's the base, the connecting, the height, delta x is just 1. So let's write those formulas out really quick. So after doing all that math, we got our trapezoid formulas here. Our total is, what is that, 16? 16 1/4? Yay. That's the area. That's what this thing equals. That's the integral. Oh my gosh. And it's positive and everything. What about this one? Can you guys do this one? 1 to 11. Ooh, let's clear the screen and let's do that one. Let's go 1 to 11. What do you guys know about the green areas? Those are negative areas, right? Yes. Come on, we've done this before. And the area above the x-axis is a positive area. And do you guys see the shapes? Do you guys see the shapes that are in here? What are the shapes that we're going to use? Triangles. All right, I'm using triangles. Okay, so it's 1/2 base times height. Those are our triangles. And I have, how many triangles do we got here? 4. So 1/2, oh dang it, I can't write right now. 1/2 base times height. I got 3 triangles. 1, 2, 3. I guess you can do this one right here and this one right here, but that's extra. Okay, let's do this. That's 1. This is 3 1/2. So I have 1 times 3 1/2 times 1/2, because 1/2 base times height. What's the height for this blue one right here? Is that 6? 6. 1/2 times the height times the base. What's my base? 1, 2, 3, 4, 5, 6, 7. So I multiply as 7. So we're going to add that, then add the next one. This would be 2, or 1/2 times base, which is 2, right? 1, 2. And then what's my height? 1, 2, 3, 4. Okay, so we got 4. Now, what we could have done, because right now what I have is not right. The way I wrote it, guys, do you guys notice that? We could say that because I counted down, this 3/2 should be negative.
That's a 3/2.
So I'm going to put...
Not a 1/2?
No, see, it goes 1 and then a half.
Oh, that's not on.
Okay, so I'm going to put a negative on the 3/2, and then same thing with the 4. And that will actually make what I'm doing correct, because this guy and this guy are supposed to be negative, right?
Yeah.
Okay. So now we do it. The first one I'm going to get 3 over 4 because, negative, plus, and then I'm going to get 3 times 7, so it's 21. And over here I'm going to get 4, negative 4. Is everybody still with? Everybody's cool? Okay, so what happens? What do I get? That is negative 4 and 3/4, so that's going to give me, if I subtract 4 from 21, that'll be 17, right? But then I have to subtract 3 over 4, so that'll be 16 and 1/4. Is that right? Yeah. 16 and 1/4. Oh, snap. Isn't that the same as the other answer?
What?
I wonder why. Oh, let's take a note from Penny over there. So it's just what Penny did. She went, hey, this guy right here, he's going to cancel out with this guy. So I'm just going to scribble these guys out. And then this guy right here, he's going to cancel out this guy.
What?
Hey, look, it's from 3 to 7, just like the previous one. And so we could have just said, oh, that's the answer. All right, so what we're doing here, guys, is we're using geometry to solve our integrals. This is possible a lot of times because sometimes they use circles or semicircles, and you guys know formulas to find the areas of those. All right? Sorry if somebody took up all your time, then oh well. Okay, this next one. I know we talked about this yesterday, but I want to put it in writing. If we are reading the interval in the graph from left to right, write that down. Left. Whoa, that's too big of a marker. From left to right. Now, reading left to right is the normal way that we read, correct? We read left to right. So then the area above the graph is positive. The area below the graph is negative. I know, you guys already knew that, right? Okay, the next one, it says, if we are reading the interval on the graph from right to left, so that's going backwards. That's going backwards. The area above the graph is negative. The area below the graph is positive, so it switches. So what would the answer to this be? Look, you see what changed? We're starting at 7 going to 3. That's going backwards. So what's our answer? Negative 16 and 1/4. We found this to be 16 and 1/4 when it's 3 to 7. So that means if you flip the lower and upper bound, the sign changes for your area. We can write an area function with integrals. Area function. Yeah, you remember how you guys you had formulas to find the area of the triangle and the trapezoids? We can write area functions with integrals, and this is how they would look. Okay, to do this, we put a variable in the upper bound. Usually that's what we do. We put a variable in the upper bound. We also need to have a different variable for the integrand, and the variable in the integration needs to be to match the variable in the integral. Whoa. Okay, that's a mouthful. Let's just draw the picture. So if I put x right here, this x the variable would be right here in the upper bound. For the integrand, we got to use a different variable. For reasons you guys will learn later, okay? They just need to be different. The lower bound is needed to know where the interval starts. So this interval starts at 3. If you plug a number in the upper bound that is lesser than the lower bound, then you will be reading the graph from which direction? Which way? Right to left or left to right? Right to left. Okay, that's just kind of a review from up there. Maybe I shouldn't have put that there. But maybe instead of saying right to left, you would just say backwards. Okay. Derivatives and integrals are inverse functions. Hey, this is fundamental theorem of calculus part 2, people. It's coming back. This means that when we take the derivative of an area function, we cancel out the integral symbol and substitute in the upper bound variable into the integrand. If the upper bound is a function, then you will need to do the chain rule. What? By first plugging in. That was a funny sneeze. By plugging in the function into the integrand and then multiplying the result by the derivative of the function. Okay, multiplying the... Wait, what did I say? by multiplying the result of the derivative of the inside function. All right. So it looks like I was running out of space, so I didn't like have an example for you guys. So let's do one together right now. Okay, the goal here is to find a prime, guys. We're gonna find a prime here. So how do we do it? Okay, there's two ways we can do this, and this is on our activity, but we didn't finish our activity yet. We'll finish that activity tomorrow. Okay, here's one way to do it. We can first use fundamental theorem of calculus and rewrite this thing. We can say that we do our antiderivative of that guy, so he would be t to the third, and then we have to divide by 3, so I'm going to multiply by 1/3. And then for the second part, we would get 4t. And you can always check your antiderivative by taking the derivative of your result and seeing if you get back to where you started. If you did, then you did it right. Okay, now I'm not going to put plus c right here because we have a definite integral, which means we need to put a straight line here. This is just notation. You don't have to write it this way. Other countries write it differently. And then I plug in the upper bound first and then the lower bound. Okay, so then I get 1/3 x to the third plus 4 times x. That's the upper bound. Minus, now I got to plug in the lower bound. We have 1/3 times, what is that? 27? 27. 27 plus 12. Make sure you use parentheses, especially because there's always a subtraction here. You need to make sure you distribute it if you are simplifying it. Okay, so 1/3 of 27, what is that? That's 9, right? And then we have plus 12. 9 plus 12 is? 21. Okay, and over here we have 1/3 x to the third plus 4x. Now later I'm going to teach you guys that this bottom number right here is what gives us the 21, right? We plugged in the 3 right here to get the 21, right? Mm-hmm. Okay. Now, let's take the derivative of this. What do we get? So let's write it all fancy, like we're taking the derivative with respect to x. The derivative of this one, I drop the 3, multiply it to 1/3, and it goes away, and I take away 1. I get x squared. This one, what do I get when I take the derivative of that? Yeah, so you guys are like easy peasy. And what happened to this constant? No one cares about him. He's a constant. He's constantly that number. His rate of change is 0. This is our answer. Now, do you guys notice anything weird about that answer? It's the same thing! It's crazy, right? So, wouldn't it be cool if there's like a shortcut to this? What if we didn't have to do all this? You guys mocking me? Okay. Shh, shh, shh. So this is our answer, right? I'm going to put it with... oops, nope, that'll mess everything up. Oh, no, go back. Okay, I'm going to say, let's take the derivative of this right from the beginning. Now tell me, guys, this x right here, where did it go? All right, so he went x to the second plus 4. And then we have a prime, because we took the derivative of the a function, so we get a prime. What happened to that 3? Why don't we care about him? Because he's a constant. So even if there wasn't a 3 here, let's say there was a negative mom down there. Okay, what does that negative mom give us? He'll give us the constant, right?
Yes.
She'll give us a okay, negative mom's bothering you guys. Let's say negative 3. Or let's say negative 7. Does it really matter what's down there? No. So when you guys take the derivative of an integral, you only care about what's up there in the upper bound. Now there are problems that have a variable on the lower bound. We will get there, and I will show you guys what to do with that. So if you guys take the derivative of an integral, it's almost like the derivative cancels that out and puts the function inside, or the x inside of it. Okay, now I got to show you guys something else. Someone just asked a great question, and I want to say it. Look at this right here. Whoops, I need a bigger highlighter. Okay, do you see this guy right here and this guy right here? Yes. This guy is before the derivative. These are the same. So actually, I could write this: that a of x equals 1/3 x to the third plus 4x minus 21. This is the same. That's the same as this integral. So we can write an integral function just as like something we're more used to. Okay, and you know what's even crazier is if you pick a number like 1. We plug 1 into this, and you do your thing to find out the area under the curve from 3 to 1. Whatever you get, that's the same thing you would get if you plug 1 into this. That's the fundamental theorem of calculus. That's rad stuff right there. So I want to take you guys back to the beginning here because I want to change things up a little bit. Instead of having an x right here, I'm going to put an x squared. I just made this into more of a function. Now before it was just the identity function, and he's kind of insignificant. He doesn't do anything. But because now it's an x squared, that changes things. Now guys, look, we have a function inside of a function. And when we have a function inside of a function, what are we supposed to do? Chain rule. So you're thinking like, oh, this must be really, really hard. No. Watch this. Okay, remember we don't care about him? Everybody say, Yeah. Okay, so x squared goes into the t. And then I'm going to multiply this by the derivative of x squared. I'll just write x squared prime. Right? You take the derivative, so you do like everything normal, and then you multiply by the derivative of the inside function. And so this would be x to the 4th plus 4. And then we have 2x. Why did I make that all weird? There we go. Okay, does that make sense? Yes. Are y'all good? Yeah. Okay, so your answer is 2x to the 5th plus 8x. This is the derivative of this integral function if you have a function inside of a function. So you got to do the chain rule. Okay, so last thing on the KiSS notes, last thing. Now you might be able to understand this. Okay, this is on your formula sheet. This function is an integral function. If you took the derivative of this, you would get g. You get g of x, what is inside of the integral function, right? You get what's inside of the integral function known as the integrand with the x plugged in. So the derivative of this is this. And so, what do you guys know about this function and how it relates to him? What does he tell you about him? It tells you his slope. It tells you, this guy tells you if he is increasing or decreasing. Does that make sense? Yeah. Okay, now what about this guy? What does he tell you about that guy? He tells you about his concavity. And guys, we can expand on this. We can go farther. We can go back to what you guys know. If I take the derivative of this guy, we will get g double prime of x. You guys with me? And what does g double prime tell you about g prime?
Whether it's up or down, the thing.
Yeah, it tells you the slope, right? What does g double prime tell you about g? The concavity. And it keeps going, guys. It doesn't stop. Now, g double prime, what does he tell you about this guy? That is known as the jerk. And yes, we can go even farther, guys. We can go here.
What is that? I don't know.
What does this guy tell you about that guy? I don't know. I forgot. Look it up.